Okay, this is another review video on a topic suggested by my student, and we are going to talk about the master theorem. And remember, before we talk about the master theorem, we have been able to solve the recursions by ourselves and using, for example, substitution. So we can do that, and the problem with the substitution is, well, every problem is a different one. So we have to solve the problem one by one. And another problem is substitution is hard. It takes a long time to do. So our question is there a general cookbook for solving recursions? And the answer is yes, and that is the master theorem. Okay, and what we are working on is a divide and conquer algorithm, and we have to figure out the Tn first. And this Tn should be, the strategy of this Tn should be, as we said, divide and conquer. So we are dividing the problem with the size n into several smaller parts, and then we solve each of the smaller parts by recursions, and after that we combine the solutions of the small part of the problem together so that we can come up with the solution of a bigger problem. So the Tn should be something like this. So we should have the Tn equals a Tn divided by b. So we are dividing the problem into several smaller parts, and then for each of them we are going to solve them, and then we're going to combine them together. And dividing the n into several smaller problem, or combining the several solution of the several smaller problem into one bigger solution, and then there could be an extra cost, and that is the Fn. Okay, so and depending on the Fn and the n to the log Bn, and we have three cases. And if we want to translate that into the easier versions, and they are case 1, n to log Ba grows faster than Fn, and then we are in the case 1. And case 2, Fn is theta n to log Ba. And then the case 3, n to the log Ba, it grows slower than Fn. And the special case for the case 3 is if we believe it falls to case 3. So if we say n to log Ba grows slower than Fn, and then we have to, before we just say it is the theta Fn, we have to first test this. We have to first test a Fn divided by b is smaller than a some constant value of the c and Fn. Okay, so we are going to see several examples. The first one is this one. So when you see recursion, the first thing we want to do is you have to figure out the a, b, and Fn. Okay, so what are the value of a, b? A is 3, b is 2, and the Fn is 3n divided by 4 and plus a 2, right? So now we have the a, b, and Fn. So the next part, what is the n to log Ba? Log Ba will give you a 1.58. So that is a little bit higher than n and a little bit lower than n squared. Okay, so remember that for the Fn is a linear polynomial to n. So n to the 1.58 is slightly faster than the Fn. So n to the log Ba is faster than Fn. So we apply case 1 here. Okay, this is the second example. So for the second example, we see a is 2 and b is 4, and then Fn is the square root of n and plus a constant number 42, right? So we want to figure out the same thing, n to the log Ba. And what is that? That is n powers 0.5. n power 0.5 is exactly the square root of n, right? So we see Fn is theta n to log Ba. Okay, so that is case 2 in this case. Okay, and let's see a harder one. How about this one? We have the a as 1, b as 2, and then Fn is n squared divided by 2 and plus n. Okay, so if we want to figure out the n to log Ba, we have n to the log 2, 1, and log 2, 1 will give you a 0, and then n powers 0 will give you a 1. So that is a constant time. So we can see n to log ba grows slower than fn because fn is n powers 2. Okay, so that is case 3. So first we can tell that is case 3, but can we really apply case 3? That's another problem. So we have to further test this one. So a fn divided by b is smaller than c of the fn. Okay, so we first want to do we want to try this part. So a is 1, so we just skip this 1 here, and then b is, oh sorry, my baby is crying. Okay, n divided by b, that is 2, right? So f n divided by 2 will be n divided by 2 squares, and divided by 2 again, and then plus a n divided by 2. That is n squared divided by 8 and plus n divided by 2. Okay, and then I'm trying to prove that it is smaller. Oops, it is smaller than c of the fn. So c is a constant value. So what I'm trying to do is I'm gonna try to increase the number 8. So I'm gonna increase the number of the 8, this number from 8 to 4. So now n squared is dividing a smaller number. So this term will be larger. So n squared divided by 8 should be smaller than n squared divided by 4. So this one is guaranteed to be smaller than this one. And what is this? That is half of the fn, right? So that is fn divided multiplied by 1 divided by 2. So what is that? So we have fn here, and then what is the c? The c is 1 divided by 2, right? So that is a constant we are looking for. So in this case, we are able to prove that a fn divided by b is smaller than this c multiplied by fn, and this c is 1 divided by 2. So that's good. This means we can really apply the case 3. So what is case 3? If you want to go back, that is theta fn, right? So this is how we can solve the master theorem. So for the master theorem, remember there are 3 cases, and this case is harder to read, so this is an easier version of the 3 cases of the master theorem. And remember, for the case 3, there is a further step you have to prove before you can really apply the master theorem case 3. Okay, that's it for this video, and good luck.